I want to start with this question. It's a 1994 question, paper 3. The first part starts out pretty straightforward. Describe an experiment to determine the specific heat capacity of a metal. Now, as I told you, if you want to find the specific heat capacity of a metal, you build the method around the equation. We know EH is equal to MC by the change in temperature. Now, we normally can't measure EH directly, as I told you. So in order for us to find EH, what we do is we find a heater, an electrical heater of known power, P, and you switch on the heater for some known time, T. So this here is really EH. And that is equal to MC delta theta. All right? And that is the key to it. All right? So in this experiment, to find the specific heat capacity, you can use an electrical heater. That's one method. All right? Using a heater of known power. So basically what you're going to do is you're going to have a block, a metal block of known mass M. You're going to punch two holes in this block. One hole to put your immersion heater, and another hole to put your thermometer. All right, you're going to drill two holes in it. You'll put your immersion heater.
I don't know.
You'll drop your immersion heater inside this hole, right? And of course, you will have connecting wires to some power supply. And you connect it like so. And in this other hole, you'll put a thermometer. Let's say that is your thermometer stick in the second hole. We can do the bulb of the thermometer.
Auntie, I want chicken.
I want chicken too.
I'm going to take something from that.
Yeah.
This is the bulb of the thermometer. It's trying to be a little bit detailed. So this so it looks like a thermometer. So this is your thermometer sitting here, and that's your power supply. So again, the heater will have known power. You'll have a stopwatch to time how long you're switching it on, and you've measured the initial temperature, final temperature, and run your ride. That's one method. The second method of doing this, and I'll not go through the second method, it's called using a method of mixtures. Second method is a method of mixtures. The method of mixtures. And what basically you're going to be doing is you're going to place the metal in boiling water, right, for a few minutes. And then you will transfer it to a styrofoam cup. That has a mass M of water with a measured temperature. So basically, I'm not going to go into too much detail in this. You have one container where the metal is boiling in hot water, so you know the initial temperature. And then you're transferring that into a second container. You have this one here that's on top of a flame. And this water is boiling. And you take your metal and you would put the metal in here. The metal will be attached by some kind of string. You put the metal in here for a few minutes, and then you will take that and transfer it to a styrofoam cup that has a little bit of water in it. This water, we're calling this mass M, and we're calling this initial temperature, let's say theta 1. So you're moving this across. This is going across here. And clearly when it goes across, because it is hot, it is going to lose heat to the water, and the water temperature is going to rise, and the temperature of this is going to drop, and you will get what we call the method of mixtures, right? So these are the two methods that you will use. Now you have to memorize these methods. You have to learn these methods because these methods will account for, if it comes in your exam, it will account for like 8 marks, you know, that kind of number. It's a big mark value for these types of questions. All right. So I'm going to clear this. And we're going to go back to the question. So that's the first part of the question. Describe an experiment to determine the specific capacity of the metal. Make clear how you calculate the specific capacity from your readings. State what precautions you're going to take to ensure the results are accurate. And that's the part I didn't mention. So what precautions you're going to take in this method? Well, one of the better precautions to take is to, you know, insulate this, right? Insulate the whole thing. One precaution. A second very advanced precaution that I would discuss with you is to start the experiment about 10 degrees below. Start at about 10 degrees below room temperature and stop about 10 degrees above, right? And that would try to, that is a very important precaution. That precaution would reduce the net heat lost to the room. It will reduce the net heat loss to the room for reasons we have discussed and we can discuss at some point in time. But that's a precaution. Start 10 degrees. Just you can write that 10 degrees below room temperature and stop 10 degrees above room temperature. And the reason is to reduce the heat lost to the room. That's the reason. All right, because once you start at room temperature, the apparatus is always going to be hotter than room temperature, and that will create a problem. That's for this experiment here, right? All right, so we okay with that. 8 marks, you see, it's a big mark question. Next part of the question: a hen incubates an egg at 38 degrees. At 38 degrees for 3 weeks until they hatch. A farmer decides to incubate some eggs. He makes an incubator, shown in figure 2. Suggest 2 methods by which the farmer can alter the temperature of the eggs. I think some parts of this missing. Outline, sorry, the first part is right here. This is part 1 here. This is part 1. Outline the mechanism by which the eggs are kept warm by the hen. That's the first thing. What are the mechanisms by which the egg is kept warm by the hen? Now, once we talk heat transfer, our general, once we talk in heat transfer, our general discussion must go around the 3 methods that heat can be transferred. The general 3 methods by which heat can be transferred is conduction, convection, and radiation. And again, to remind us of a definition, conduction is the It's the movement of heat. All right. Conduction is the movement of heat through a medium from areas of high temperatures to areas of low temperatures without net movement. We also know that convection proceeds via two mechanisms. One of the mechanisms of conduction is lattice vibration. And the second mechanism is what? Electron diffusion. We can expand on these two mechanisms. That's conduction. What is convection? Convection is the movement of heat through a fluid. By the net movement of the fluid. And we have to understand that convection proceeds, the reason for convection is due to density changes. So when you heat a fluid, for example, it becomes less dense and it rises. All right, and the opposite is true. When you cool a fluid, it contracts, it becomes dense, and it sinks. So you have these two methods by which you have movement. And of course, radiation is of course, from areas of high temperatures. Areas of low temperatures, right? And this it can move through a fluid, it can move through a solid, it can move through a gas, and it doesn't even need a medium. So one of the differentiating things, this is the definition for radiation, all right? It is the movement of heat by electromagnetic waves, all right? It's different from the other two, as recall, because it can even take place in a vacuum, all right? So these are the three methods. So once we have to discuss something on heat transfer, we need to be able to remember these definitions, and we're reviewing it very quickly. I want to give you a visual reference. So in that context, we can talk about this. Well, hold on. Let's talk about this question then. Why is it not coming across? What's the problem? Right. Oh. And it's gone. Let's try it one more time. It's horrible, horrible. Can't see what's going on there. Image. All right. So what are the mechanisms? At least we have, I don't like that image. I'm going to delete this. Sorry. I'm going to do it another way. So this will be better. Yeah, it's much better. All right, so how does the hen keep this egg warm? The first one we said we're trying to answer under these three sections. How does the hen keep the egg warm in conduction? And I want to change the color so we can differentiate, right? And the first thing in conduction, if you ever look at the underside of what we call layers, the underside of layers, they have no feathers. So the hen keeps the egg warm by directly conducting body heat to the egg because the body is touching. So when they generate heat, they transfer that heat directly by conduction to the egg, all right? Because the egg is touching the bare underside. Right? So that's how it participates in conduction. In convection, well, there's another part with conduction. That's the first part of conduction. The second part of conduction is the eggs are placed on a straw bed, and straw is a bad conductor. So the heat cannot leave, and the hen, whatever heat leaves, the hen would, provide that heat that is being lost. And of course, convection. Well, what happens to the hen is when they sit on the egg, they will fluff up their feathers, so you can't even see the egg. So the hen So the hen would fluff up their feathers around. So you wouldn't be able to see. If you ever seen a hen on top of the eggs, you hardly ever see the eggs because it's under them, completely under them, and the feathers, they cover it from all sides. All right. So these are the methods by which the hen keeps the egg warm. Two points in conduction, 1 point in convection. Radiation doesn't take place because, as we know about radiation becomes more significant. Radiation is a significant radiation only becomes significant at high temperatures. At low temperatures, radiation therefore is negligible and could be neglected. At room temperatures, you don't really consider much or significant amounts of heat being transferred by radiation. So we okay with that. Next part. Outline the mechanisms, two mechanisms by which a farmer can alter the temperature of the eggs. Well, that's pretty straightforward because the farmer is using this incubator. And if I wanted to, for example, increase the temperature of the eggs, you can simply use a brighter bulb, right? And if the farmer wanted to reduce the temperature of the eggs, he can, by slightly opening that's a couple methods that the farmer could employ. You can use a brighter bulb, or you can not only use a brighter bulb, you can also increase the voltage of the bulb. You can increase the voltage of the bulb. You can increase the power supply that's running to the bulb. That will make the bulb brighter, deliver more heat, and therefore cause the temperature to increase. So these are two methods that the farmer can employ to do that. Right. And explain how each method works. And I went on to that. I clarified that, how each method works. This last part here is to do with the next area that we have to study. Let me just copy this out. All right, so we have this information here. So let's see if we can make it a little bit bigger. Right. All right, so let's analyze this. Each egg in the incubator has a mass of 0.6 kilogram. Now, before I go into there, we're dealing with heat transfer again, and we remember the equations for heat. There are two equations for heat. EH is equal to MC delta theta EH is equal to MC delta theta. And of course, there's a second equation for EH that we've spoken about. And that is EH is equal to ML. That's LV, LF, vaporization or fusion. These are the two equations that we look at when we're dealing with heat energy. In this question, the whole MLF is not needed because in this question, there is no vaporization going on here. There's no vaporization going on. The heat is being used to change the temperature of the egg. So let's read it. Each egg in the incubator has a mass of this and a specific capacity of that. In order to keep the eggs at a constant temperature of 38, each egg must receive heat at a rate of 3 watts. So we have our egg. And the question is saying something rather perplexing. And what is rather perplexing is, in order for us to keep the egg at a constant temperature, we have to supply heat to it. We have to supply heat. We have to actually supply heat to keep the temperature constant. What does that mean? If we have to supply heat to keep the temperature of the egg constant, what does that mean? Help me, somebody. If you have to supply heat to keep the temperature constant, let's say you have a bucket, all right? You have a bucket, and in order for you to keep the water level constant, let's say you had to keep pouring water into the bucket, right? Let's say you had this container that you left on the stove or on the sink, and every day you come, you realize the water level has dropped, so you have to add some water to keep the level constant. What does it mean? What does it tell you about the container? It tells you that with the container, talking about the container, you have this container, you place this container on your sink, you fill it with water, you mark the level, but when you come in the evening, you realize the water level has dropped. So you will have to top it up to bring it back to this level. What would account for the fact that you have to top it up? You have to keep adding to keep the level constant. So this thing must have some kind of small leak where a small amount of water is leaking, or evaporation could have been taking place during the course of the day. All right, two reasons. Either evaporation, in any event, you have a situation where water is leaving the container. In the same way, this egg, by saying each egg, I know I was moving all the place. By saying this, that you have to supply heat to keep the temperature constant, the question is telling you that this egg is losing heat at a rate of 3 watts. It means 3 joules every second is leaving. That's why you have to supply 3 to keep the temperature constant, because it's leaving. And this temperature remains constant. That's the condition, right? So each egg must receive heat at a rate of 3 watts to keep the temperature constant, meaning if you were not supplying this heat, the temperature of this would drop. And it's going to drop because it's losing 3 joules every second, right? So we understand the situation with the egg. Even though there's insulation, even though they have the box is closed, you still have to provide heat 3 joules every second to keep the temperature fixed at 38. So we understand that. If the lamp was switched off, now if the lamp is switched off, what does it mean? If the lamp is switched off, it means we're not supplying any heat anymore. But it is still going to be losing heat. So if it is losing heat, the temperature would not remain at 38. Because it is losing heat, the temperature is going to have to drop. So we appear that. If the lamp is switched off, how long will it take the temperature of the eggs to fall to 36? So what we have is, again, EH is equal to MC delta theta. So we can write EH is equal to M. They gave us the mass of the egg, which is 0.06 kilograms. They gave us the specific heat capacity, which is 4,000 joules per kilogram. It's already in kilogram. It's already in kilogram. Multiplied by the temperature change. And the temperature change that they're working with is from 38 to 36. So this will be multiplied by 2. And this is going to be equal to P. And P is the same rate of loss of heat. It's losing 3 joules per second. That's power multiplied by how long it will take. The question is, how long? How long will it take? So this is really the question here. So at that point, it becomes a simple question of solving the equation. Once you analyze the thing, it becomes a simple question of solving the equation. So T would be equal to all of this. T would be equal to all of this divided by 3. All right? Brad, do you see that's 4/8? Divided by 3? I'll say yes or no. 160. That's 1/60 seconds. Okay? We understand that? Clear, everybody? Feedback, feedback, feedback. Any part of it you want to ask, clarify? Okay, Bradley. All right, good. Awesome. All right, let's go on to another question. Is there any other question, any other topic any other question in thermophysics that you want me to go to? Because this question, if you realize, this question covers two sections. It covers these equations and it covers heat transfer. So in that sense, it's an important question to know how to work. All right. But the question is there any specific question in thermal that that you can look at in your handout and say, well, I want this work, I'm not sure about this type of question. Give me feedback on that, please. That's no, well, I'll go on to the next type of questions I consider. Oh, let's talk about this very quickly. This is the 1997 question. When you drill a hole in a metal, the drill bit becomes very hot. How could you explain this observation using the 18 caloric theory? Now, we learned that there were two theories of heat. One of the early theories of heat is called the caloric theory. And the caloric theory believed that heat flowed from a hot body to a cold one by means of a massless fluid called caloric. Heat flowed because of a massless fluid called caloric. The modern theory is where heat is a form of energy, and this was developed a combination of Count Rumford and experiments done by Joule. All right, this was the old theory. This is the modern theory. So these are the two theories. The first one, why does the drill bit become hot? The caloric theory says the drill bit becomes hot because when you're drilling out metal, you release caloric, and that caloric flows into the bit and gets the bit hot. But the modern kinetic theory says that when you're drilling out a hole, the drill rubs against the metal and friction causes heat energy to be produced, right? You'll understand that, or you want me to write that down for you? Tell me what you need. You understand that verbatim, or you want me to write that down for you? Remember, this is going to be taped. This is being taped and it's going to be deposited and write it. Surely, sure. Right, so I just outlined the two theories, right? So now I'm going to get into the answer because you have a basis for dealing with the answer. So first of all, why does the drill becomes hot? Due to the caloric theory. Right? You good? That's what the caloric theory would have explained. And the second one is the sorry about my typing. Right? So that's it in a little more detail. Right. So that's how did the evidence from Count Rumford experiment in drilling barrels of cannon convince scientists about the theory? And what Count Rumford found? Count Rumford found that drilling with a sharp bit produces less heat than a dull bit. And his explanation was that the dull bits, if you think of a sharp knife and a dull knife, and you want to cut something with a sharp knife, you can make one pass and two pass, and you can cut something with a sharp knife. But if you have a dull knife, you have to rub it back and forth more times, not so. And because of that, the dull bit would have more passes before it can cut through the cannon, and therefore there'll be more friction, and it would produce more heat, but it wouldn't cut as effectively. All right, so that was Count Rumford's observation. Right. Use the kinetic theory to explain why a melting solid, to explain the melting of solid at constant temperature, even though when it's heated. And why is it that a solid remains at constant temperature when it is changing state, when it is melting? And the reason is when the melting point is reached, the heat transferred, the heat supplied to the solid is used to do what? Anybody? Sure? Come on, type it. Heat transfer to the solid is used to do what? is used to break bonds, right? It is used to break bonds. This is almost visible. The heat supplied to the solid is used to break bonds. But I guess before we can write that, we should say that temperature is proportional that first the temperature is proportional to the kinetic energy of the molecules. You know this. So the faster the molecules move, the more kinetic energy it has. So temperature is proportional to the kinetic energy of the molecule. When the melting point is reached, the heat supplied by the solid is used to break bonds, and we can add that's what happens. When you reach melting point, you're supplying heat, but instead of the heat causing the molecules to move faster, the heat is being used to break bonds. So no heat is used to increase the kinetic energy. So the temperature remains constant. Right? So that is the explanation as to use the kinetic theory of heat to explain the melting of a solid at constant temperature once it's heated. You're supplying heat, but the heat is not increasing the kinetic energy of the molecules. It's just being used to break bonds. The same thing happens at the boiling point. Right? Same idea. The heat is being used to break bonds between the liquid molecules. Right? Right. This next question is another EH is equal to MC delta theta and MLZ. I think we've done a fair amount of those questions. And I really want to look at something in gas laws. So I guess we can take a look at this 1999 question. Well, this one is an interesting question. A really interesting question. It has a combination. It's not gas laws. It's a specific capacity latent heat. I somehow felt we did this, did we? Did you do this question on one of the Saturday classes? No? All right. So let's go through this. Describe an experiment to determine the latent heat of vaporization of water. All right? How are we going to determine the latent heat of vaporization of water? Again, once you have to come up with an experiment, you should always find the appropriate equation. All right? And the equation in this case for the latent heat of vaporization is EH is equal to M LV. So the method to find the latent heat of vaporization of water is we take a container and we place this container on a scale. We place a container on a scale. And in that container, we want to put some water. There's some water in there. And then we're going to get our favorite immersion heater. We're going to get an immersion heater. and we're gonna drop the immersion heater in it. Of course, the immersion heater would be connected. Oh, sure. The immersion heater would be connected by wires. Always draw this right. It must be connected by wires to some power supply. That's how it's getting its energy. So that's an immersion heater. All you need now is a stopwatch. All you need now is a stopwatch. Now what you do, what's the procedure? You switch on the heater and you wait. You wait until the water is boiling constantly, and simultaneously you record the mass and start the stopwatch. Simultaneously, as you record the mass, you start the stopwatch. You then wait, keep the stopwatch running, keep the boiling process going. For, let's say, 5 minutes or 10 minutes, at which time you stop your stopwatch. You stop the stopwatch, and at the same time, simultaneously again, and you record the mass empty. You record this initial mass, but you normally give it a symbol. You call it M1, and M2. And this will be T time for 5 minutes. Once you've done that, it's just a matter of putting everything into the equation. The equation is going to be PT, because we have the heater of known power P. I should put that in the method. Switch on the heater of known power P, right? So we have PT is equal to M1 minus M2 in this case, because the change in mass multiplied by LV. So to work it, LV is equal to P multiplied by the time, but the time, of course, must be converted to seconds. Simple. So that is a method to determine the latent heat of vaporization. P by time in seconds divided by the change in mass. Eight marks. You see it? 8 marks. Every time they come, that's the kind of marks that we normally give them. Now, teachers generally don't like to give this generally. They don't like to give this because it requires a lot, it's a lot harder to mark this type of question, because you have to basically mark something like an essay. Physics teachers tend to want more numerical or short-worded answers. But different teachers have their own peculiarities, but that's a general thing. Part B. The body loses thermal energy in several ways. One is by warming the air taken into the lungs and then breathing it out. A second way is by evaporation of water into the air, which is then exhaled from the lungs. In one breath, a girl inhales a volume of this at 25 and this air is warm to 37. The mass of air inhaled, what is the mass of air inhaled and how much thermal energy is transferred? Again, what is the mass of air inhaled? To get the mass of air inhaled, you all have this question in front of you, or do you all have, this is supposed to be in a thermal physics heat question handle. Do you have it in front of you? Just know yes or no. Just tell me yes or no. Without that, do I look for it? No. Okay, some people have it, some people don't. I'm going to just put this piece here that I'm working with. In fact, this whole thing. I'll copy this so I can paste it in here. So you can see it at the same time. When I bring it across all these x to the, m cubed becomes m3 instead of that. That's a problem. And the multiplication sign becomes something different. Okay, so we can work it now. Immediately we see the first part is blah, blah, blah. What is the mass of air? What is mass? Mass, in this case, they gave us the volume, not so. And down here, they're giving us the density of air. Mass is equal to volume by density. And that will be equal to 4 by 10 to the minus 4. Because that's a volume, right? Multiplied by the density of air, which is 1.2. So Bradley will give us that number. That is 4.8 by 10 to the minus 4, Bradley. Too slow. 4.8 by 10 to the minus 4. Bradley, you got up to that one? Bradley going for lunch, church? Yeah, boy, Bradley. Bradley, go on.
I think he's still here.
Well, his machine on, but he's not responding, so you're probably sleeping or eating. Bradley, actually, sitting out.
Yeah.
All right. I forget he was across the room eating food or something, or playing a video game. All right, so that's the math, right? You clear on that? I say yes. You clear on that? Yep. Okay. So that's the mass. That's the first part they want us to find. What is the mass of air inhaled? And the second part is how much thermal energy is transferred to the air. How much thermal energy, EH, is equal to what? Why are we using MC delta T? Because we're not changing state. It is air coming in and air coming out. So it's not changing from solid to liquid or liquid to gas. So that's why we will use this form of the equation. And in here we have 4.8 by 10 to the, all right, over all that. Now we have all of this. Oops. That's M multiplied by the specific heat capacity of air was given. The specific capacity of air is 1 by 10 to the 3. And the temperature change is from final temperature was 37 and the initial temperature was 25. And from there, we can get, we can work on that part. Part 2. A mass of 1.8 by 10 to the minus 4 kilogram of water vapor is exhaled along with the air for each breath. So they're telling us, apart from the air being heated, you're actually producing water vapor. You're actually producing water vapor in the lungs. Now, water vapor, to vaporize air, you're really giving off heat. All right, 5.76 Bradley. So apart from heating the air, you're also producing water vapor in the lungs. So how much heat is given off? Calculate the thermal energy required for the water vapor to evaporate. Again, this is part one. Part two, for the water vapor to evaporate, again, we go EH is equal to MLV. And they're telling us is 1.8 by 10 to the minus 4. Multiplied by the latent of vaporization, which they gave here, as 2.5 by 10 to the 6. And how much is that, Bradley? So let's not fall asleep again. 450. Do you know that you'll exhale water vapor? Do you know that? Like when you're in a cold place, if you're in a cold place, right? Like, and you were to breathe out. Have you ever seen mist being produced when you breathe out in your cold place?
Yeah.
Right? You see people talking, and when the place is cold, you actually see like smoke coming out from them. What happens is they exhale water vapor. And if the air outside is cold, the water vapor immediately condenses to tiny droplets of water. All right? So that's the water vapor that comes out. This is it here. It is coming out as vapor, but if the air is cool on the outside, the water vapor cools very quickly and becomes tiny droplets. It looks like you're speaking and mist coming out from your mouth. That's evidence that when you exhale, you're actually exhaling water vapor. Along with the air, you're exhaling water vapor. So that's part two. Part three. In 1 minute, a girl takes 12 breaths. What is the average total energy loss per minute? Now, this is one exhale. This is one exhale. All right. So the total energy in one breath is 450 plus 5.76. So without a calculator, we could figure out that's 455.76 or 0.8. I'll just use the whole number. This is how much energy is exhaled in each breath. But this girl is doing how many breaths per minute? 12. So the energy in 12 breaths would be equal to 12 multiplied by that. And that will give us the answer for that next part. 1 minute a girl takes 12 breaths. What's the average total energy loss per minute as a result of breathing? Right? Yeah, 5,469. Again, when we write answers, we have to write it to the appropriate number of significant figures. And you see this data is given to 2. So we should try to make our answer, although this is the one we see on the face of the calculator, we should make our answer into 2 significant figures, which would be 5,500. Okay. Otherwise, you're likely to lose marks. But I suggest you put both values. I suggest you put this and you put that. So your teacher, you know, if you just put this, they might say, hey, you didn't get the right answer for some strange reason. You know, sometimes things go that way. So yeah, that's that question. We good. Simple, clear, no problem. That's a yes, that's a no, that's a maybe. Come on. Yeah. Next question. Another topic that the question, the exam, you could get in the exam is gas laws, as I said. So that's the last question we'll do today. Find a gas law question. Like this one. State Charles' law. Charles' law says volume is proportional to Kelvin temperature. Describe the ACE diagram and experiment to test the validity of Charles' law. We should know what those diagrams look like. That's a yes or no. Do you know what this diagram look like? The Charles' law apparatus. Charles' law apparatus. Do you know what it looks like? All right. So we weren't going to spend time on that. The cylinder shown in figure 2 is fitted with a freely sliding piston containing a gas. Again, gas laws is a basic thing. It's basic because all we have to do is to populate this equation. That's all we have to populate that equation. We just have to remember the biggest mistake that students make is we must convert to Kelvin. We can't work in degrees Celsius. It must be converted to Kelvin. So if I could bring back up the question, the cylinder shown in figure 2 is fitted with a freely sliding piston containing an ideal gas of mass 13 gram and volume this. The temperature of the gas is 25. Now this law is only valid provided that mass is constant. That's the only way. Mass must be constant. A cylinder shown in figure 2 is fitted with a freely sliding piston containing an ideal gas of mass 13 gram and volume that. The temperature of the gas was 25 and was initially at atmospheric pressure. So let's see if you could put that information on this question. T1 is equal to 1 atmosphere. V1 is 1 by 10 to the 4. And that's cm cubed. And T1 is given as 25 degrees Celsius, but we must convert this to Kelvin, which is 298 Kelvin. We have to use it in Kelvin. So we have the initial information here. The gas is heated to a temperature of 400. What is the new volume of the gas? Now, because this is a freely sliding piston, part here says it's a freely sliding piston, meaning that if you were to heat this gas, the pressure will increase and it will push the piston up. That's why it's a freely sliding piston. The piston is not locked. This piston could move. The important thing is the pressure acting here is atmospheric pressure, and the pressure of the gas will always be atmospheric pressure. So this pressure of the gas is in fact a constant. The pressure of the gas is in fact a constant. They want us to find V2. And given that they're heating it to a temperature of 400 degrees Celsius. 400 degrees Celsius, we have to convert it to Kelvin again. which will be equal to 4 to 673 Kelvin. So it's just a matter of saying that V1 over T1 is equal to V2, which we don't know, over T2. And solve. Pretty straightforward, not a problem. All right. So that's how we get the new volume. That's part one. Get the new volume. Part two, how much energy must be supplied to the gas to raise its temperature to 400? Well, again, if they say how much energy, they're talking EH, right? EH and in the question, they gave us M, and down here they gave us C, and we know the temperature differences from 25 to 400, that's 375. You see, this one is joule per gram, right? And this is 13 grams. So we don't have to convert them to kilogram. We could use them because they're both matched already. All right. The temperature difference, you don't have to convert it to Kelvin. You can, if you convert, I mean, if you were to subtract these two numbers, you will get 375. If you were to subtract, take this away from that, you will get 375. And if you were to subtract 25 from 400, you will get the same 375. So it doesn't, you don't convert the difference. You have to convert the actual values and then subtract. This will give you the heat energy. Part of the energy becomes kinetic energy of the gas particles. State the effect of the remainder of the energy. When you, this is a trick part here. This part is a trick part. This is an A-level question, this part here. We don't normally teach you this in CSEC level. But what happens is this. When you supply heat, some of the energy goes in the molecules moving faster, so the temperature goes up from 25 to 400 degrees Celsius. But you see, when this piston is pushed back, what happens is the gas is pushing up on the piston. The pressure of the gas multiplied by the area of the piston, pressure by area is equal to what? Force. So the gas is exerting a force on the piston. And at the same time, the piston is moving up. This entire piston is moving up to a new location up here. So the piston is having a movement, an upward movement of X. What is happening is some of the energy that you supply, yes, goes into making the molecules move faster, but the remaining energy is being used to cause the gas to expand. To do work, sorry, by the way, to do the remaining work, the remaining energy is used to do work against the atmosphere in the gas expanding. So when the gas expands, the gas is pushing back the atmosphere. And since the gas is exerting a force and a force is applied over a distance, force by distance, the work done against the atmosphere is F by X. The work done against the atmosphere is Fx. So back to the question. I'll read again. Part of this energy becomes kinetic energy of the gas particles. State the effect of the remainder of the energy. And the remainder of the energy, as I'm saying, is being used to do work against the atmosphere when the gas is expanding. Right? And the last part, if the volume of the gas kept fixed during the heating, what will be the pressure at 400? Then we're going back to the same thing here. If the volume was fixed, let me just copy this. They're telling us now if the volume was fixed. In other words, this volume is not unknown. This volume is the same initial volume. And the thing is, the pressure, P2, is now the unknown. So the equation becomes P1, because the V's will cancel out, P1 over T1 would be equal to why? Because the volume here and the volume here is the same. And therefore they will cancel out. So again, it's pretty straightforward. P2 is therefore equal to P1 by T2 over T1. P1 is 1 atmosphere multiplied by T2, which is 673 over 298. And whatever number Bradley gets first there, that will be in atmospheres. I'm Stony Joe boy. I gotta buy a calculator for Bradley, you know. Aye, 2.26. Thank you, Bradley. 2.26. You get that? Was Alicia who went? Not sharp. 2.26 atmospheres. That's the answer. Everybody got on that? And that, ladies and gentlemen, is where we end at 2:26. Yeah, boy, she blazed you. All right, so that's a review on thermophysics. We covered what we covered. We covered methods of heat transfer, conduction, convection, radiation. We covered calculation using MLV. We covered methods of determination of specific heat capacity, method of determining latent heat of vaporization, a whole host of things we covered. Of course, that doesn't, in 1 hour and a half, we can't review the whole section, but we've done a significant part of it. So you would need to continue your process, do a little more work so that you'll be comfortable for the exam. All right, so I've set you on a base. So you need to put in a couple more hours on this to get any level of comfort on it. All right, so I'm seeing you all when is the next session? I'll put everything down the timetable now. We have a session tomorrow from 3 o'clock, for those of you who can make it, 3 to 5:30. All right, so those of you can make it. A few then try to put in some work. What I really want is for you to try questions at home and find out which one you can't work out. You see, once we know which one you can't work out, having spent some time and tried it, then I could really help you more than I could help you by doing what I'm doing here, which is working questions for you. and discussing it. So work a few questions this evening. The ones you get stuck in, bring it tomorrow, and we will deal with it. Okay? So good evening, everybody. Remember, it's time for me to go on break. So I'll see you all tomorrow. Ending session. Goodbye.